The dynamic earth, mass wasting processes. Objectives. After attending this module, the user should be able to comprehend the importance of mass wasting processes on the planet Earth. It is one of the silent processes that is happening on the surface of the Earth. The module also highlights the various kinds of mass movements and their impacts on land. Introduction. Earth's geomorphological processes are never-ending activities. The landforms are formed due to various endogenous and exogenous processes. The endogenous processes are generated by the internal forces of the earth. They are the tectonic processes like earthquakes, deformation, volcanic eruptions, metamorphism, and seafloor spreading. The exogenous processes are activated by the geological agents acting on the surface like running water, moving glaciers, blowing wind, and washing sea waves. In addition to these, there are some natural geomorphic processes acting on the surface of the earth. They are the weathering and mass wasting processes. These two processes are very active on the surface of the earth. They are responsible for many morphological modifications of rock bodies existing on land. Among these, mass wasting is a unique geomorphological process destabilizing the surface rocks and soil mass. Moving mass on the Earth's surface. Gravity pulls the rocks, soils, and debris on a downward slope naturally without any chemical change. This downward movement is called as mass movement or mass wasting. Landslides, mudflows, and rockfalls are all belonging to this category of geomorphic processes. In this lesson, the following aspects of mass wasting are highlighted. Mass wasting and its causes, types of mass movements, triggers of mass wasting, factors influencing mass wasting, importance of mass movements. Mass wasting and its causes. The term mass wasting is used for a broad category of processes whereby the Earth's surface materials are pulled down on a slope by the force of gravity. Mass wasting is a geomorphic process by which soil, regolith, and rock move down a slope under the force of gravity. It is also called as mass movement. It happens on a standing rock body or regolith. It is closely related to weathering, which is the breakdown of minerals or rocks at or near Earth's surface through physical, chemical, or biological processes. It is also related to erosion because the transport of material is done through a variety of agents like wind or flowing water. Forces for movements. There are two forces involved in a mass standing on a slope. One is the driving force, and the other one is the resisting force. The standing mass has the driving force due to its weight. The slope and substratum have the resisting force. When the driving force exceeds the resisting force, then the mass becomes unstable and moves down or falls. When the gravitational force acting on a slope exceeds its resisting force, failure of slope occurs in holding the mass. Slope materials. The slope material's strength and cohesion and the amount of internal friction between material help in maintaining the slope's stability. These are collectively known as the slope's shear strength. The steepest angle that a cohesionless slope can maintain the mass without losing its stability is known as its angle of repose. When a slope possesses this angle, its shear strength perfectly counterbalances the force of gravity acting upon it, and the mass will not leave. When the angle of repose is more, with a little trigger or disturbance, the mass moves down rapidly. Slow rate. Mass wasting may occur at a very slow rate, particularly in areas that are very dry or those areas that receive sufficient rainfall such that vegetation has stabilized the surface. It may also occur at very high speed, such as in rock slides or landslides with disastrous impacts. Varieties of mass wasting happen based on the type of mass involved, type of movement involved, and the type of effect they create on a region. These movements are classified according to the speed and force of the process, from extremely slow creep to very rapid, dramatic slide or fall. Factors responsible. The factors that can change the potential of mass wasting include change in the slope angle, weakening of the material by weathering, increased water content, changes in the vegetation cover, and overloading. Role of water. Water plays a typical role in mass movements. Water can increase or decrease the stability of a slope depending on the amount present not only on the overlying mass but also on the slope. Water may help to create a slippery phase on the slope. Small amounts of water can strengthen soils because the surface tension of water gives the soil a lot of cohesion. This allows the soil to resist erosion better than if it were dry. If too much water is present, the water may act as a lubricant, accelerating the erosion process and resulting in different types of mass wasting like mudflows and landslides. Sandcastle. A good example of this is to think of a sandcastle which may collapse at any time. Water must be mixed with sand in order to form the castle to keep its shape. If too much water is added, the sand washes away. If enough water is not added, the sand falls and cannot keep its shape. Types of mass movements. Types of mass movement are distinguished based on how the soil, regolith or rock moves downslope as a whole. The process involves two major factors as type of mass and type of movement. The type of mass involved may be bedrocks or soils. The type of movement may be a fall, slide, flow, or creep. Subcategories of mass movements. In addition to these, subcategories of mass movements are classified based on the type of movement involved as planar movement or rotational movement. Types of mass wasting. Types of mass wasting include creep, slides, flows, topples, and falls, each with its own characteristic features and taking place over time scales from seconds to years. The downslope movement of material, whether it be bedrock, regolith, or a mixture of these, is commonly referred to as a landslide. Under a complex situation, all of these processes generally grade into one another, so classification of such complex processes is very difficult. Types of mass movements. Ultimately, the classification results into the following types of mass movements: creeps, slides, slumps, flows, falls. Creeps. Creep is a long-term mass-wasting process on a downhill. In this process, the combination of small movements of soil or rock occurs in different directions over time. Creep is directed by gravity gradually downslope. The steeper the slope, the faster the creep. The creep makes trees and other shrubs bend and curve to reach the sunlight. These often trigger landslides because the dirt underneath is not very strong. The trees most of the time die out because of lack of water and sun, and these rarely happen in wet climates. Slides. Slides are sudden downhill movement of masses of rock or sediment or soils. Slides are also called translational slides as they involve only straight movement along a direction. Rock slides and debris slides result when rocks or debris slide down a pre-existing surface such as a bedding plane, foliation surface, or joint surface. Piles of talus are common at the base of a rock slide or debris slide. Slides differ from slumps in that there is no rotation of the sliding rock mass along a curved surface. Landslides. Landslide is a general term used to describe the downslope movement of soil, rock, and organic materials under the effects of gravity and also the landform that results from such movement. Landslides can be classified into different types on the basis of the type of movement and the type of material involved. The material in a landslide may be either a rock or soil or both. Slump. The term slump refers to a slipping of coherent rock material along the curved surface of a decline. Slumps are also called as rotational slides due to the type of movement involved. These are special category slides wherein the downward rotation of rock or regolith occurs along a concave, upward curved surface. The upper surface of each slump block remains relatively undisturbed, as do the individual blocks. Slumps leave arcuate scars or depressions on the hill slope. Slumps may be isolated or may occur in large complexes covering thousands of square meters. They often happen due to human activities. Slumps are common along the roads where slopes have been oversteepened during construction. They are also common along the riverbanks and seacoasts where erosion has undercut the slopes. Heavy rains, tectonic disturbances, tremors and earthquakes can also trigger slumps. Flows. Movement of soil and regolith resembling like a fluid behavior is called as a flow. These include avalanches, mudflows, debris flows, earth flow, lehers, and sturzstroms. Water, air, and ice are often involved in enabling this fluid-like motion of the material. Sediment flows. Sediment flows occur when sufficient force is applied to rocks and regolith that they begin to flow downslope. A sediment flow is a mixture of rock and or regolith with some water or air. They can be broken into two types depending on the amount of water present as slurry flows and granular flows. Slurry flows. Slurry flows are sediment flows that contain between about 20 and 40% water. As the water content increases above 40%, the slurry flows grade into streams. Slurry flows are considered as water-saturated flows. The slurry flows are further classified into solifluction, debris flows, and mud flows. Granular flows. Granular flows are sediment flows that contain between 0 and 20% water. Granular flows are possible with little or no water. Fluid-like behavior is given to these flows by mixing with air. Granular flows are not saturated with water. Each of these classes of sediment flows can be further subdivided on the basis of the velocity at which flowage occurs. Solifluction. Solifluction is a flowage of soil mass at rates measured on the order of centimeters per year of regolith containing water. Solifluction produces distinctive lobes on the hill slopes. These occur in areas where the soil remains saturated with water for long periods of time. Debris flows. Debris flows occur at higher velocities than solifluction. The velocities may range between 1 meter per hour to 100 meters per hour. It often results due to heavy rains, causing saturation of the soil and regolith with water. They sometimes start with slumps and then flow downhill, forming lobes with an irregular surface consisting of ridges and furrows. Mudflows. Mudflows are very different type of mass movements. These are a highly fluid, high-velocity mixture of sediment and water that has a consistency ranging between soup-like and wet concrete. They move at velocities greater than 1 kilometer per hour and tend to travel along valley floors. These usually result due to heavy rains in areas where there is an abundance of unconsolidated sediment that can be picked up by the streams. Thus, after a heavy rain, streams can turn into mud flows as they pick up more and more loose sediments on the way. Mud flows can travel for long distances over gently sloping stream beds. Because of their high velocity and long distance of travel, they are potentially very dangerous types of mass movements. Mud flows can also result from volcanic eruptions that cause melting of snow or ice on the slopes of volcanoes or draining of crater lakes on volcanoes. Volcanic mud flows are often referred to as lahars. Some lahars can be quite hot if they are generated as a result of eruptions of hot tephra. Granular flows. Granular flows are yet another type of mass movements. Creep is a very slow, usually continuous movement of regolith downslope. Creep occurs on almost all slopes, but the rates vary. Evidence for creep is often seen in bent trees, offsets in roads and fences, and inclined utility poles. Earth flows. Earth flows are usually associated with heavy rains and move at velocities between several centimeters per year and hundreds of meters per day. They usually remain active for long periods of time. They generally tend to be narrow, tongue-like features that begin at a scarp or small cliff. Grain flows. Grain flows are usually formed in relatively dry material, such as a sand dune on a steep slope. A small disturbance sends the dry, unconsolidated grains moving rapidly downslope. Debris avalanches. Debris avalanches are yet another type of mass movement. These are very high velocity flows of large volume mixtures of rock and regolith that result from complete collapse of a mountainous slope. They move downslope and then can travel for considerable distances along relatively gentle slopes. They are often triggered by earthquakes and volcanic eruptions. Topple. Topple are unique instances when huge blocks of rock pivot and fall away from a slope. Topple failures involve the forward rotation and movement of a mass of rock, earth, or debris out of a slope. This kind of slope failure generally occurs around an axis or point at or near the base of the block of rock. A topple often results in the formation of debris or a debris cone at the base of the slope. This pile is called a talus cone. New talus cones don't have any plants growing on them. Old talus cones can have weeds and even trees on them. A rock fall may be a single rock or a mass of rocks, and the falling rocks can dislodge other rocks as they collide with the cliff. A fall, including rock fall, is where regolith cascades down a slope but is not of sufficient volume or viscosity to behave as a flow. Falls are promoted in rocks which are characterized by presence of vertical cracks or joints. Falls also occur due to the undercutting action of water as well as undercutting of waves near coastal regions. They usually occur at very steep slopes such as a cliff or escarpments. The rock material may be loosened by tremors or earthquakes, rain, plant root wedging, and expanding ice. Talus. The accumulation of rock material that has fallen down will reside at the base of the structure. It is known as talus. Because this process involves the free fall of material, falls commonly occur where there are steep cliffs. At the base of most cliffs, we get the accumulation of fallen material called as talus. Factors influencing mass wasting. The major factors responsible for mass movements are shear strength of mass, slope of the land, weathering and climate, water content of the mass, vegetation, overloading, geology and structure, thickness of the soil cover, and triggering mechanism. They are seismic shaking, increased overburden from structures, increased soil moisture and infiltration of water, reduction of roots holding the soil to bedrock, undercutting of the slope by excavation or erosion, weathering by frost heave, and bioturbation. Tectonic causes. The most common triggering mechanisms are strong vibrations from earthquakes and excessive amounts of water from a winter snow melt or a heavy rainstorm. Volcanic eruptions, explosions, and even loud claps of thunder may also be enough to trigger a landslide if the slope is sufficiently unstable. Many avalanches, which are rapid movements of snow and ice down steep mountain slopes, are triggered by the sound of a loud gunshot, a sonic boom from a supersonic airplane, or, in rare cases, even a person's shout. Role of gravity. Mass wasting is generally related to gravity. Creep, slides, and flows. All of these processes share one thing in common, namely that they are caused by the incessant downward pull of gravity, which moves all loose slope material downwards. Gravity-driven mass wasting processes are a subset of larger set of processes that transport weathered and unweathered earth materials. The trigger for mass movement may come due to microseismic activities, tectonic dislocations, and shaking of the ground by neotectonic forces. Such incidences may be common in places where there is an active fault on a hill slope. Overweight. The second triggering mechanism is the increase in the weight by a overburden. It may be a new structure created on the slope involving a heavy weight. Sometimes, cutting the slopes for laying roads and dumping the excavated mass on another slope may increase the weight. Overloading is almost always the result of human activity and typically results from dumping, filling, or piling up of material. The additional weight created by overloading increases the water pressure within the material, which in turn decreases its shear strength, thereby weakening the slope material. Role of water. Water has hydraulic pressure. When water enters into the soil, it fills the pore spaces of soils and weathered zones. Due to this accumulation of water molecules on the regolith and soils, the weight increases. It also starts moving down through the pores. Water can create slippery phases between the bedrock and the overburden. The amount of water in rock or soil influences slope stability. Large quantities of water from melting snow or heavy storms greatly increase the likelihood of slope failure. The additional weight that water adds to a slope can be enough to cause mass movement. The mass movement may occur after any slow and steady rainfall. Throughout the world, the water-induced mass movements are more in number. Rainfall is the major triggering mechanism. Role of vegetation. Vegetation affects slope stability in several ways. By absorbing the water from a rainstorm, vegetation decreases water saturation of a slope's material, and the resultant loss of shear strength that frequently leads to mass wasting. The removal of vegetation by either natural or human activity is a major cause of many mass movements. Removal of trees may affect the binding mechanism between overburden and the bedrock. Roots of trees have the ability to keep the mass intact on a slope. Growth of trees. Growth of trees is a slow and steady natural process, and hence it never triggers a mass movement but does the opposite. It binds the mass with the bedrock. Due to incidences like forest fires, such unexpected conditions arise. Erosion is a major triggering mechanism. It forcefully removes the mass down a slope. Sometimes, the undercutting action of flowing water along a slope may move the surrounding rock bodies and regolith downwards. Similarly, cutting of slopes for highways or constructions may also lead to this situation. Weathering is another process enacting mass movements. Weathering has the ability to disintegrate the overburden and decompose the mass both physically and chemically. These physical disintegration processes may loosen the mass. Once the compactness is disturbed, then the other factors like water saturation takes a lead role to move the mass. Though weathering is a slow process, it induces the mass to move even on a gentle slope. Root wedging. Root wedging is a different process. Through cracks and fractures, the roots penetrate and destabilize the rock block below. Such actions may encourage rock falls and debris falls. Bioturbation. Bioturbation is yet another factor for mass wasting. The role played by microorganisms may loosen the compactness of the mass on a slope. Slope failure. When the gravitational force acting on a slope exceeds its resisting force, slope failure or mass wasting occurs. The resisting forces helping to maintain slope stability include the slope material strength and cohesion, the amount of internal friction between grains, and any external support of the slope. These factors collectively define a slope's shear strength. Slope angle. Opposing a slope's shear strength is the force of gravity. Gravity operates vertically but has a component acting parallel to slope, thereby causing instability. All slopes are in a state of dynamic equilibrium, which means that they are constantly adjusting to new conditions. The greater a slope's angle, the greater the chance for mass wasting. A number of processes can oversteepen a slope. One of the most common is undercutting by stream or wave action. This removes the slope's base, increases the slope angle, and thereby increases the gravitational force acting parallel to the slope. Excavations for road cuts and hillside building sites are another major cause of slope failure. Grading the slope too steeply or cutting into its side increases the stress in rock or soil until it is no longer strong enough to remain at the steeper angle and mass wasting ensues. Weathering and climate. Mass wasting is more likely to occur in loose or poorly consolidated slope material than in solid bedrock. As soon as solid rock is exposed at the Earth's surface, weathering begins to disintegrate and decompose it, thereby reducing its shear strength and increasing its susceptibility to mass wasting. The deeper the weathering zone extends, the greater the likelihood of some type of mass movement. Geology and slope stability. Geology and slope stability are to be considered. The relationship between topography and the geology of an area is important in determining slope stability. If the rocks underlying a slope dip in the same direction as the slope, mass wasting is more likely to occur than if the rocks are horizontal or dip in the opposite direction. Importance of mass movements. Mass wasting is an important part of the erosional process, as it moves material from higher elevations to lower elevations, where transporting agents like streams and glaciers can then pick up the material and move it to even lower elevations. Mass wasting processes are occurring continuously on all slopes. Some act very slowly, others occur very suddenly, often with disastrous results. Any perceptible downslope movement of rock or regolith is often referred to in general terms as a landslide. Conclusion. Rapid mass wasting events such as massive landslides or debris flows are typically triggered by events that destabilize material that resides on steep slopes. Such events include earthquakes, volcanic eruptions, rain or melting snow, and poorly planned landscape alterations by humans. The road cuts or developments that require the removal of material at the bases of slopes may lead to slope failures. The impacts of mass wasting could be seen only on the hill stations and roads along the ghat sections. Landslides are serious hazards along these roads. Frequent maintenance of these roads becomes an expensive affair for any government. Knowledge about the relationships between local geology and mass wasting processes can lead to better planning of a region that can reduce the vulnerability of such natural hazards.